half-wave rectifier working. Today we will discuss about the derivations. So first step of the derivation. So for any, it might be any derivation. It might be in this thing. The first step will be instantaneous signal. Instantaneous signal. That means you have a sine wave, which is an AC signal. So how you are going to represent this AC signal in mathematical equation? So we will represent it as Vi is equal to Vm sine omega t, or this can also be written as Vm sine theta. So Vm indicates the peak value. If you take this one, or this portion is called peak value, this portion or this portion. See, if you are taking this portion, that is the positive side, that is above the reference level, then it is plus Vm. If you take downwards with reference line, that is minus Vm. So plus Vm and minus Vm. So here, so this I have already explained what is Vm, sine, why we take, and omega, all those things in the last class itself. So we directly move on to the derivation. So whenever you take any signal like this, so this is our input signal. So Vi. So when you pass this signal at the output, this is the output we are having. Okay, so in positive half cycle we are getting the output. In the negative half cycle it is completely zero. So current will not flow because the diode is reverse biased. For this purpose, first thing what we are going to derive is DC, or average current, that is IDC. IDC is what? The amount of DC content in this output. This is the output. In this, how much DC content we are having, and I have already told you we can represent a signal either in voltage form or in current form. For both, the waveforms will be same. For both, the waveforms will be same. Okay, so first we are considering average DC current or average current. So when you find average current by using Ohm's law formula, V is equal to I into R, even we can convert, or we can get the voltage formula also, or the voltage equation also. Okay, so DC or average current, this is the first derivation what we are going to do. In same way, before going on to this, I had written Vi is equal to Vm sin omega t. In the same way, if you want to represent this signal in terms of current, then you can write it as Ii is equal to Im sin omega t, or Im sin theta. Okay, so both voltage and the current both can be represented in mathematical form like this. Suppose I know Vm value, but I want Im value. So I know Vm value, but I want Im value. So during that case, what we have to do? We have to take V is equal to I into R. So V is Vm, I is Im, R is RL. So then Im is equal to Vm by RL. This is the formula we are having. But in our half-wave rectifier, what are the other what are the components we are using? What are the components we are using in our half-wave rectifier circuit? Diode, then load resistance, transformer. See, these three things are we are using. Okay. Now, when you are using a diode, does the diode have some resistance in it? It has some resistance, right? That resistance is known as RF, forward resistance. It offers some resistance. In the beginning of the class, while telling you 0.7, 0.3, I was telling you the junction offers some opposition. That opposition is nothing but resistance. That resistance is forward resistance. And we are having the transformer. What is the transformer basically made up of?
It transfers the current.
Yeah, fine. I'm
Medium.
asking you, what is it made of? Transformer, what is it made up of? What does a transformer contains?
Sir,
Coil.
silicon.
Resistance.
Coils, right? It contains coils. It is made up of coils. See, in diagram only we represent it like that only, no? Like this.
Primary, secondary.
Primary and secondary. That means their transformer is made up of coils. So coil means what kind of coil? What it is actually coil means? It's a metal, right? It is a metal, copper we'll be using for coiling purpose. Does this metals have resistance in it?
Yes, sir.
Obviously, it will have resistance, right? That resistance is Rs. When you are going to consider that current is going to flow in the circuit, then it has to overcome forward resistance, it has to overcome the resistance of this coils, and also it has to overcome this load resistance. So my equation becomes now Im is equal to Vm by, what is the total resistance we are having in the circuit now? RL plus RS plus RF. All of you understood how we got this equation? Why we are writing it as RL plus RS plus RF?
Sir.
Okay. Now, suppose in one of the problem, they'll give the problem like this. There is an half-wave rectifier circuit which is made up of an ideal diode. Find the peak current where the peak voltage is this much, load resistance is this much, like that they have given. In that case, what you are going to do? For RF, they're telling an half-wave rectifier is made up of an ideal diode. During that time, what will be our RF? What is the resistance offered by ideal diode for forward bias?
So 0.
0. So during that time, RF becomes
0.
0. Okay. And one more thing, if in the question, in later in the problems, we'll get it. I'm just telling now only. If in the problem, if they're not mentioning the resistance of this coil or the source resistance, then ignore it. Okay. Then your formula will be Vm by RL. Can I ignore RL?
No, sir.
No, sir.
No. Why? Why?
Because there, it will always have some resistance.
Yes, it is a load where we want the output to come. I'm connecting a mobile to my charger, my adapter. My mobile is a load. Without that load, I cannot expect the voltage to exist there. Right? So we cannot ignore it. Okay, this is about the basic things. How we got VM, all those things. Okay, now come back to this derivation. So in the derivation, the first step is area, sorry, average DC current is equal to area under the curve over full cycle divided by time period. Area under the curve over the full cycle by time period. So area under the curve means we need to talk about this one, average DC current. Can I call this as a curve? Is it a curve?
Yes, sir.
It is a curve. So according to the formula, area under the curve over full cycle. Full cycle means starting from here to here. So what is the length of the cycle?
0 to 2 pi.
0 to 2 pi. So totally I can take the length is 2 pi. But here area under the curve over full cycle they are talking about. Area under the curve over full cycle means we have the curve only for this much duration. So you need to consider only this area. Can I consider anything here? We cannot consider because there is no curve. It is completely zero. So now what I will do is this for this particular thing, area under the curve over full cycle, I am going to write first step is 0 to 2 pi Im sin theta into d theta divided by time period is 2 pi. What I will do is 0 to 2 pi is the length for full cycle. I will split it up. 0 to pi Im sin theta into d theta plus pi
Pi to
to
2,
2
2
pi Im sin theta d theta whole divided by 2 pi. Now, do we have any current? Do we have any current? So if you get confusion, you can take this as I naught only. So this becomes your Im. Okay. So do we have any current from 0 to pi? 0 to pi we have current. Is the current flowing from 0 to pi?
Sir.
0 to pi the current is flowing.
Flowing.
So retain it as it is 0 to pi Im sin theta into d theta plus from pi to 2 pi
No
to
current.
2 pi, no current. So it becomes 0 divided by 2 pi. That is equal to 1 by 2 pi 0 to pi Im sin theta into d theta. So now take Im outside, Im by 2 pi outside, integrate sin theta. So when you integrate sin theta, you will be getting minus cos theta 0 to pi. So this becomes Im by 2 pi of cos pi minus cos 0. So minus will be outside. So we'll just continue here. So this will become minus Im by 2 pi of minus 1 minus 1. So that becomes minus Im by 2 pi of minus 2. So this to become plus 2 will get cancelled and we have Im by pi. So IDC is equal to Im by pi. This is the formula. If you want to write what is the value of pi? 22 by 7. If you substitute that 22 by 7, you can write it as 0.318 Im or you can stop it here only. Okay, this is the formula for the average DC. In the same way, average DC current, in the same way, we can have VDC, average DC voltage. So according to Ohm's law, VDC is equal to IDC into RL. Now we know already IDC formula just now we found. IDC is equal to Im by pi into RL. So it is, we are having it VDC. So whenever, you should remember one thing, whenever they ask you to find DC voltage, you should if you have VDC here, you should have VM here. If you have VDC here, you should have VM here. See, in the last equation, what we had, IDC is equal to Im by pi. Here also we have current, here also we have current. The same way, but here we are having V, here we are having I. So now what you have to do, we have to convert this Im to what?
VM.
So to convert Im to VM, we have already have a formula, right? In the beginning, Im is equal to VM by RL plus RF plus RS. So VM by RL plus RF plus RS into RL by pi. When you compare RL with this RF and RS, load resistance will be always very, very high compared to the forward resistance of a diode and the resistance of the coil. So on that basis, what we can do is, we can write RL plus RF plus RS is approximately equal to RL. Okay, it is approximately equal to RL. So that's, in that way we can write VM by RL into RL by pi. RL get cancels, VM by pi. So that is equal to, therefore VDC is equal to VM by pi. Okay, so RF and RS are very, very small compared to RL. That's why we are writing the entire term as RL. But in the problem, in the exam or anywhere in the problem, if they have given you, if they have mentioned RF value, RS value, then you have to consider that. Suppose in the problem they have not mentioned anything, forward resistance or the source resistance, they are not mentioned, then you can ignore it and you can directly take RL. But if they have given, you have to take RF, RS. If they are not given, ignore it. Okay, so this is the equation for average DC. Okay, now we have seen this was the input which is given to the rectifier, and we are getting the output like this. The whatever the output we are getting, is it a DC output we are getting? Is it a pure DC we are getting? Is it a pure DC? What is pure DC? How the pure DC should be? How should be the pure DC?
So straight line.
Straight line, right? But what we are getting?
Rectifier.
Right? That means whatever we are getting, it is not
Pure
completely
DC.
DC. It is it contains, even though we tell output is rectifier, it converts AC to DC, but the output is, it is a mixture of AC and DC. Okay. So output, because of this shape, we tell that it contains AC. Only in AC we can have this possibility. If you are having DC, then it should be straight line. So we can, this shape or whatever the arc shape we are getting, This kind of shape indicates that output contains a AC content. So in short, we tell presence of AC content in DC output is called ripple. It is called as ripple. Okay, next we we derive an equation for ripple. So in short, presence of AC content or AC component in DC output is known as ripple. See, these are all ripple. Someone will ask you, show me the ripple. This is a ripple. Because I want, actually I was expecting a straight line. I'm getting this kind of thing. So it is a ripple. Okay. Now the next one, root mean square load current, that is IRMS. Last we derived average current or DC current. Okay. Now I want to find out the average AC current which is present. When we pass it, we get like this. And here I told you it is having presence of AC plus DC. But I want the average of this AC. Average of this AC. Just a minute. Hello. Is anybody having any doubt? Okay. Now I want the average of this AC component. I got the average of DC component. I want the average of AC component. So that's why what I'll go for root mean square load current. Why would we want this root mean square load current? See, you are in engineering, you should know, if you're doing something, you should know why we are doing this. See, I have a bulb. Okay, I have connected it to the supply. So this is an AC supply. I want to know what is the average current it consumes. What is the average current it consumes? Since it is AC supply, I cannot find the current directly. Can you tell me why? Average I cannot find directly, or I cannot tell exactly this is the current it uses. It's a simple common sense question I'm asking. AC supply is there, but I cannot tell directly that this is the current it consumes. Based upon, I'll tell, see, this is the signal which is flowing to this. Tell me the average current it consumes. Assume that you don't know anything about the bulb and don't tell that it will be printed on the bulb only. Why you want to find all these things? You don't know anything about that. I'm giving you a bulb. There is nothing printed on that. You are connecting it to AC supply. I want to know what is the average current it consumes. Why I want this, or why we want to do something to find this. In the question itself, answer is there. In the diagram itself, answer is there.
Due to too much fluctuation in current.
Why it will have fluctuation?
Because it's AC,
Because it has
AC supply.
Yes, it's a AC supply. It is continuously varying. I was telling you, no, AC have n number of values.
dynamic.
Dynamic. It is keep on changing. It is a dynamic curve. It is keep on changing. When you and for 1 second it is at 0.5 ampere, it 2 seconds it will be 0.1 ampere, like that it is keep on changing. If you take voltage 0.1, 0.2, 0.3, 0.4, it is keep on increasing, decreasing. It happens continuously. But we don't have this problem in DC because it is constant. We can tell, oh, 5 volt, yes, 5 volt it will consume because it is giving 5 volt only always. But in AC, it is not like that. So that's why we want to find out average. What is the total average? Average means it gives you some base, or we'll tell no everywhere. On an average, this will be the thing. On an average, this much we walk. On an average, this much we eat. Right? So it gives a kind of threshold. So that threshold for the average current of an AC signal is known as root mean square load current. If I am asking you what is the AC current which is present in the output, then you should tell RMS value. RMS value will give you that AC content which is present in the DC output. Okay, to find the average of it, we are going for RMS value. RMS always deals with AC. It doesn't deal with DC. Please remember this. Many of the time, actually you don't have the experiment, but if you are in electronics domain, we do these experiments in third semester. We have electronic devices lab. There we do this experiment, and we'll tell the students to take the IAC, that is AC current, as IRMS, because that is the RMS value is the AC current only, average AC current. So now I think you got an idea why we need to find this RMS value, to know the average AC current. So for this also, the first step is same, but first step means the RMS is equal to area under the curve over the full cycle by time period, that will be same. But here the extra thing is root and square. So everything is written, everything is given in the heading only. RMS value is root. So you'll have a root. Mean square. That means, so whatever we had written, no, the previously 0 to 2 pi Im sin theta d theta, to that you'll add square. Im square sin square d theta. What we had written there, 0 to 2 pi Im sin theta d theta. Here it is square. Okay, root mean square, root mean square. So that is the additional thing we are having. So now steps we will be keep on doing 1 by 2 pi. Again we split up 0 to pi im square sine square theta into d theta plus, okay, we'll take 1 by 2 pi common, pi to 2 pi im square sine square theta into d theta. So again, what is 0 to pi? Do we have current?
Yes, sir.
From pi to 2 pi? Do we have current from pi to 2 pi? No current.
No.
So this tends to 0. So the remaining equation is root of 1 by 2 pi 0 to pi im square sine square theta into d theta. So now I'll be taking im square common 0 to pi sine square theta into d theta. So we know for the sine square theta, it is, what is the formula? 1 minus cos 2 theta by 2. Zero to pi 1 minus cos 2 theta by 2 into d theta. So after that we keep on simplifying it. M square by 2 pi 1 by 2 0 to pi d theta. We have taken 1 by 2 outside minus 1 by 2 cos 0 to 0 to pi cos theta 2 theta into d theta. So after that we integrate it. I think the mathematical steps you can understand. 0 to pi. So and after doing all those things we arrive with root of im square by 2 pi into pi by 2. So pi get cancels and he'll be having im by 2. This implies IRMS is equal to im by 2. This is the formula for IRMS. Same way for VRMS, steps are same. VRMS is equal to IRMS into RL. Again, IRMS we have got im by 2 into RL. I want VRMS, I have VRMS here means I want VM here. So I will substitute for im. So that is VM by 2 into RF plus RS plus RL into RL. So what we tell, again we know that RS plus RF is very less compared to RL. So VM by 2 into RL into RL. RL get cancelled and we have VM by 2. So that is VRMS. VRMS is equal to VM by 2. This is the formula we are having. See, this derivation is same for all. Half wave rectifier, full wave rectifier with center tap, bridge rectifier. For all same steps, but only the thing is here we get the output only for 0 to pi. There along with 0 to pi even we get from pi to 2 pi. Both will consider. Here also IM will consider, there also we will consider. But here we consider this as 0. That is the only change, but steps are same. This is for the root mean square value. So after this root mean square value, the next one we are having is ripple factor. So ripple factor is the quantitative measure of conversion of AC power to DC power by a half wave rectifier. That means it is going to tell you how much AC content is present in the DC output. By this we can tell, so my output, whatever I'm getting in that output, this is the amount of DC content it is present, because it contains both AC and DC. If I tell, suppose if I tell 70% of output, just read this sentence and tell me the answer. 70% of the output is AC. That means what is the DC content? How much percent is the DC content?
30%.
30%. Okay, so that 70%, whatever we are telling now, this is your ripple factor. This is going to tell you the ripple factor of a given output. Okay, this is what we are going to find, how much content it contains. So based upon finding out how much ripple factor it contains, then we think about how to filter out this AC. Then we use a capacitor to filter out this AC. That's what we study later in the later topics. So how to filter out this? To filter out this, I need to find out how much is the AC content. So here, for this, the first step is R is equal to, small r is nothing but ripple factor. RMS value of AC component of output voltage divided by DC component of output voltage. So R is equal to RMS value of AC component. I was telling in the last case only. RMS value is nothing but AC or DC value. AC. It is almost AC. So we take R is equal to IAC by IDC. We are telling RMS value of AC component. That's why we take IAC. So we have one more equation for RMS value. I RMS square is equal to I square DC plus I square AC. See, we among this, for which parameter? See, 1, 2, 3. We are having 3 parameters here. Among these 3 parameters, for which we have an equation. For which parameter we have an equation?
IRS.
No, I'm asking R,
Person.
IAC, IDC.
IDC.
So we don't have, even though we tell IRMS is nothing but almost IAC, but we don't have direct equation for IAC. We have only equation for IDC. We don't have, we are not representing an equation with IAC. So we have only equation for IDC. To find an equation for R, we need an equation for IAC. So what we do is, we take this equation and we rearrange it.
IRMS by I
is equal to root of I square RMS minus I square DC. Now you substitute here. When you substitute here, you'll get R is equal to root of I square RMS minus I square DC divided by IDC. What we'll do, we'll take IDC inside the root. So we get IRMS minus I square DC by I square DC whole roots. So that is equal to root of I square RMS by I square DC minus 1. Okay. So now after this, the next step, you'll be writing here root of I RMS by IDC whole square minus 1. That is equal to root of IRMS by IDC. What is the formula for IRMS? We have derived now. IM by 2. What is the formula for IDC? IM by pi minus 1. So common terms cancel. We get root of pi square by 4 minus 1. Use your calculator and find out the answer such that you'll be getting 1.21. Okay, 1.21. So if you have opened the textbook, actually it is 121%. There is a dot present there. You just change it. It is 121%. It is printed as 1.21%. Actually, in the next part and all, it is corrected 121% AC component. There, by mistake, it is 1.21%. It is 1.21 factor is correct, but when you convert it into percentage, it is 121%. So 121% means, what does it mean? The majority of the output is what? AC. So whatever we have thought the half wave rectifier is going to rectify and give out. So in that given out output, the majority component, whatever we are seeing is AC. Okay. So by knowing this, we are going to find out what is the how